We don't have very many. Um, so there are no products that perform the same function as us specifically, but there are some that do sort of the same thing. Um, there are photo light sensors already on the lift terminals, but they don't perform the same function that ours does. All it does is make sure that the bar is up as it comes through the terminal to pick up a passenger, because if the bar is down, they won't be able to sit and they'll get run over by the lift. So that doesn't necessarily do anything that would directly compete with us. And then there's also this magnetic backpack for children. What happens is they wear this giant magnet on their back, and then when they get on the lifts, they activate an electromagnet on the chairs, which stick them to the back of the chairs so that they can't move. So whether or not the bar is up or down is irrelevant because they can't get out of it. And then as soon as the skis hit the ground, the magnet releases, and then they get off and they just spread up safely. This is only implemented in some places in Europe, and so far no place in the United States has done it. Okay, and here is a block diagram of our system. So we have the power supply, which has some blocks in it of itself, and then that goes to the microcontroller, and then each one of our sensors. So we have an audible alarm, which is in the form of a speaker that just beeps at you, an RF transmitter, which if we sense that somebody is in the chair and they have their bar up for a determined amount of time, then we'll transmit it back to the base stations, and they can pull their pass, yell at them, give them some sort of warning. We also have the motion detector and the switch, which the switch is actually the motion detector is dependent upon the switch. The motion detector will not be in use until the switch is up.
So this is our motion detector, that black thing over there, which is actually the white thing on the actual prototype. It's a passive infrared sensor, so what it does is it sees infrared light and senses when there's a change in the infrared light. It doesn't actually send out infrared signals like most other sensors. So basically it's a motion detector. It detects 7.5 inches of movement up to 2 meters away. So that's pretty much as far as the chair is going to be. The sensor in actuality would be above the heads up as far as the chair goes and looking down at the people. So this is our circuit that is going to send a signal to the microcontroller. This is the switch, which if it's open, obviously none of this is going to be working, so there's going to be no signal sent to the microcontroller, which would serve as a logic 0. And then if the switch is down, which means the bar is up, the sensor is going to be working. We have the output, which is going to be a digital 5 volts is going to be buffed. And then it goes through an RC time constant, which is 10 seconds, which just kind of, since the motion detector only sends out a signal when it's detecting, it doesn't just give a constant voltage when a person is there. We kind of had to manipulate this a little bit so that when a person's there and there's a lot of movement, it's going to be a logic 1 sent to that, so that's why we have this followed by a comparator. So if there's a lot of motion, the voltage is going to generally be high, and then that gets sent to the microcontroller. So this is our switch. It's a magnetic reed switch. It has 2 pieces. One has the leads coming out of it, and one is the actual magnet itself. And when they come close enough to each other, it will be connected, so it's just a wire. And then when they go far apart, which is greater than 33 millimeters, which is like, it's like an inch, they will disconnect. So when the bar is up, they will see each other, and the switch will be closed. And then when the bar is closed, the switch will open up and disconnect the sensor, and then send the logic 0 to the microcontroller telling to send the alarm off.
Okay, so for our alarm system, right now, since we still are in the prototyping stage, we are weighing our options for how to do the audible alarm. this right now is what we have implemented. It's not nearly as effective as we would like it to be. The alarm is not very loud, so we want to get a piezo buzzer, which we could just use the microcontroller to power because it'll take a DC voltage to power it. We also have LEDs. Right now, they are solely on the microcontroller, but we're going to use some of the unused pins from the microcontroller to drive LEDs through some type of LED driver. Computer gets to implement. And okay, so here's the power supply block diagram. So in the conditions on the mountain, there's only one type of battery chemistry which would be able to hold up in those temperatures, and that's nickel cadmium. And nickel cadmium batteries have a characteristic called memory, which makes it so that if they aren't fully discharged before you recharge them, they will not have the same capacity as they originally did. So I designed a smart charger to go and look at the level of each one of these batteries and decide which one should be in charging and which one should be in discharging configuration. So we can take a look more at the specifics of those. So obviously, since we can't run power, we are going to be running solar. This is our solar design, or our solar product that we're using. The trickle charger is kind of tricky to design, and where we have so much other stuff to do, we decided to go with a commercial product. So it has the solar panel, it has overcharge protection, and it has a trickle charge so that it will correctly charge the batteries at a current that is safe. Here is a schematic diagram of our logic circuit. So there's two comparators, which we'll look at next, that monitor the level of the batteries. And once they reach a certain threshold, they will activate, and they will send logic levels to the controls on this quad analog switch. And so what's going to happen is at all times one will be on and the other one will be off. And so one of the battery packs will always be connected to the solar charger, and the other one will always be connected to the circuitry. And they'll only switch when the logic levels change. And here is our comparator circuit. There are two of these, one to monitor each one of the batteries. So in multi-sim, I used a voltage supply and a potentiometer to simulate the effects of battery draining. And once it reaches the threshold set by this Zener diode right here, it will activate and send out a logic high to it'll send out, a logic high to our quad analog switch. And so we had that breadboarded, we got it to work, and here is our layout. It's also right here.